I really want to focus on Microsoft because I'm actually, after doing more research into it, I was actually really, really fascinated with what Microsoft did and the approach they took and why it's such an interesting step into the quantum sphere. I will do my best not to try and keep it simple and not get super technical. But if you have questions or things like that, send them to me afterwards and I'll try and clarify or give additional details. But I now am even more intrigued by where Microsoft is. Not so much on the, oh my gosh, is this, what does this mean for things? But what Microsoft pulled off is a very interesting and yet controversial step in the quantum space, in that they actually, so while everybody else was in such a hurry to do quantum computing, which like so many people are, they're just in a hurry to do it. They kind of are like, we'll clean up the mess later. And if you don't know much about quantum computing, that's okay. But if you've ever seen videos of it, there's like this really cool, like steampunk chandelier thing that goes along with it. And you're like, ooh, what is, and it's hard to understand, like, what is that chip and how does it fit into there? And it has to do with the instability of the quantum sphere and the fact that when you start dealing with quantum mechanics and particles that are potentially in infinite states all at the same time, it's extremely unstable. And so you have to go to great lengths to try to stabilize the environment to prevent anything from disrupting it. And that's one of the major problems with quantum computing is under traditional, the traditional way of doing it, which I think is superconducting qubits. Okay. And you can go back and look at what the definition of qubits is, but essentially it's a particle that's instead of being in the 1 or 0 state, it's in infinite states all at once. And typically the way many of the chips have gone is this superconducting qubit. They're creating superconducting qubits. It's a different manner by which doing it, but it's extremely vulnerable because these qubits are sitting along a line, and even the slightest disruption in a particle, a magnetic field, anything can just throw it off, which is why there's so much noise when it comes to things, and why when you try and scale quantum computing, it's very difficult because you have to have so many of these things working because so many of them are getting disrupted and messed up all over the place that you've got to now do this across millions of qubits to hopefully get one that's successful. So you can see it scales very poorly when it comes to some of this stuff. And so that's why you've got this steampunk thing, because it's trying to keep it down to as close to absolute zero as it is, so that molecules are literally almost not moving. They suck all the air out of it, so it's a vacuum. I mean, it's absolutely fascinating. If you're not a tech nerd, I won't keep geeking out on it because you might be going, I don't even know what you're saying and I don't understand, whatever. But it really is fascinating to see the lengths they have to go to with this. So I was curious because Google had successfully done this, and Google and Microsoft aren't the only two in the space. There's others, IBM, and there's other big players doing it. But many of them have been taking this different approach. And Microsoft has been working on this for 17 years to really focus on this whole idea of the Marjiana particle, which in essence is less vulnerable, in that one of the risks is with typical quantum particles, qubits, there's a positive and a negative charge. And as a result, it's very vulnerable. Okay. It's very vulnerable, which causes a lot of these errors. And the Marjiana particle has been a theoretical thing where it was like, what if we could create a particle that actually was stretched out across, and I know I'm going to butcher this. So if you're a technical person, you're probably going to be like, Christopher, that's not exactly how it works. Like, yes, I know, but it stretches it out and spaces it out in a different way so that it's actually, you can punch a hole in it and it doesn't blow the whole thing up. So the one example that people have used a lot is, if you tie a knot in a rope, you don't disrupt the knot no matter what you do to the rope, so long as you don't mess with the knot. And essentially what the Marjiana particle does is spreads this thing out so that you have less of a chance of cutting the knot itself. Versus the other ones, the knots are like right there, and all it takes is something to hit that knot and boom, it blows up the whole thing. So Microsoft, rather than just saying, how do we force quantum computing and then we'll clean up the noise later, said, let's actually figure out a better way to do quantum computing. And let's take the time to find a more stable way of approaching quantum computing. And that's really where the Marjiana particle came into play. Now, granted, this thing isn't new. I don't have my notes up right now, but like it was theorized. I don't remember where it was, like a long time ago, like a long time ago, but they haven't really been able to prove it. And that's where when Microsoft came out and said, we did it, like we actually successfully created this stable Marjiana particle that's operating it's creating a quantum qubit. It actually doesn't have all the noise that it has. Now, if I remember right now it's only 8 of these particles operating off the current chip. But they wanted to perfect this way of actually doing quantum processing, because then instead of having to scale, okay, well, if we do it with 1,000, we actually need 10 billion of these quantum particles because there's so much noise. We need 10 billion to get 100 that are accurate. If we get the Marjiana particle right, we can say, well, I mean, if we have 8 and really 8 or 7 of them actually remain stable through the whole process, through the whole compute, we don't need to scale up to 10 billion of them because it scales better. And so that's where this is a pretty significant development. Now, if you read stuff, you'll see people get really upset about it. They're like, that's not exactly, we still aren't sure that it's working the way they're saying it is. But it's actually, and the technical term is, it's a topological qubit. So it's a different way that it works on the, what's the term I'm thinking of? The superconductors. Anyway, I don't want to get too technical for the sake of losing all of you. If you want to know more, let me know, or there's plenty of other resources from folks who probably are far more eloquent at explaining this stuff. But essentially, it's a far more stable way of doing quantum computing. And so now what this does is potentially, right, they still got to prove it more, and they're still taking all the heat from everybody, and everybody's like, how is this actually going to do what you said it's going to do? But it seems as though they've actually made a major breakthrough, which actually this would be the first one, to my knowledge, that I could find that actually has taken this approach to quantum computing. So it still allows it to do the quantum computing in a much more stable way. Still requires a lot of the cool steampunk stuff to make it happen, but it is far less unstable, which means it's easier to scale. You have less noise, you have less room for error. It really makes quantum computing much more feasible, assuming this all goes according to plan. And on top of it, then what's really exciting about this is by doing this, we're actually going to be able to see this as moving out of the theoretical scientific world. Because right now we're still very much in the scientific world of this. How do we do qubits, and do we do topological? Do we do superconducting? Do we do trapped ion? Which one's the best? And right now it's looking like the topological, this Mariana particle, is much more stable, much a better way of doing it. If that proves to be the case, we're going to start to see the quantum computing space take off significantly, because I was watching one interviewer who was talking with the Microsoft engineers on this. And if this really truly is what they're saying it is, the real advantage to this is that this now becomes an engineering challenge versus a scientific one. So now it becomes a matter of, okay, now how do we scale this? How do we make it more feasible to actually, make this more accessible to people? How do we democratize the capability? All this other stuff. And so this could be really exciting. And that's where, to me, when I looked at it at first, I'm like, okay, somebody else is kicking around, another quantum device. It's not as groundbreaking as I thought. Then when I started digging into it and seeing the way they approached it, which doesn't surprise me with Microsoft, that's the approach that they would take, it could change things. Now, a lot of people are like, so what? I mean, what is this actually going to do for anything? Now, I'm not going to sit here and talk at length about all the possibilities of what quantum computing could do, because there's plenty of other people doing it. And honestly, it's way still too early to tell. While I say, if this in theory is accurate, it does move quantum computing into a new sphere that makes it an engineering challenge rather than a scientific challenge to solve. We've still got a long ways to actually, scale, bring this into a sphere that people can actually use, apply it in different ways. But one of the primary ones that I think we're going to start to see this start to move very quickly is in chemistry. And largely because of the fact that trying to understand molecules and particles and how they interact with each other and chemical reactions and all this stuff is very, very, very complicated. It's very difficult. It requires a ton of computing power to calculate and model the sometimes seemingly infinite possibilities for all the different factors that can come into play when it, just as a simple example, if I were to say, what are all the possibilities of drinking this spindrift in my body? And it's like, I don't know, like what medications are you on? Like, what's your body composition? What time of day did you drink? You start thinking about these things and trying to isolate what happens when I consume that becomes an infinitely difficult problem to solve. Now, if you think about companies trying to manufacture and create new particles or new products or things like that, and they're trying to figure out how could we possibly know the implications of this thing. It's a computing problem. Well, if we can get quantum computing up and running, it suddenly becomes a lot easier to start to do some of the analytics and research into, okay, what do these compounds do? And when we mix them together, what happens with this? And here's all these other variables. Now model this out so that we can hopefully see further into the future and predict what might go wrong with this, what might go sideways, what things might we need to consider, so that instead of waiting until it happens and we go, oh crap, we put asbestos in everybody's house. Who would have thought? We can go, all right, if we do this, this is going to happen. You know what? We just need to cancel the whole thing, or we need to find a different way, or we need to create a different compound to be able to pull this off. So right now, that's where a lot of people are looking to what they're going to be able to do with quantum computing. There's countless other use cases, but I just wanted to kind of, again, highlight the significance of Microsoft's quantum chip, break it down a little bit more. Like I said, the biggest thing to note is it's a far more stable way of creating qubits, which means less noise, less risk, easier to scale, all this other stuff, and ultimately transitions it into an engineering problem, in theory. To the critics out there who are going to send me messages and tell me, no, Mike, I saw the, yeah, I know. I'm not saying this is the end of things for all the competition. I'm just saying it's an impressive breakthrough, to say the least.